Welcome, STEM students. We're on day 3 of waves, and today we're talking about interference. If you play guitar, if you play an instrument, you'll know some of this already, but we'll show you some things, and we have a video that's going to go with this. I tried to make a link into the video, but that didn't work, so by the end of this, by the time this is posted, hopefully we have something that is quality. So I have to disappear here for a second because the notes will only play when I'm off the screen. So here we go. Okay, so interference. Interference is when waves meet and they either add together or they tear each other apart. Now, if you look at this, if you can see my mouse, I have a little cursor here. This first wave here, it's above the resting position. So say this was a string or a spring and you sent a wave through it. We used to do it with the hose, the garden hose when I was little. My brother would be on one side, I'd be on the other side. We'd send waves at each other trying to hurt each other like brothers are supposed to. And so anyway, we have this wave coming towards the center, this wave's going towards the center. And this diagram on this side is supposed to be when they meet. And so when they meet, the red and blue aren't really supposed to be there. They join and they form a new, bigger wave, right? That's called constructive interference. It builds together. It's constructed, right? Also, if the waves are on opposite sides of the resting position, say one is up and one is down, and they cross. Now the green is supposed to be what happens when they cross. The red and blue disappear, right? So it cancels itself out. That's called cancellation, also known as destructive interference. Now, you may have heard of cancellation because if you have some headphones, you might have noise-canceling headphones. It's exactly what noise-canceling headphones do. They take the sound from the environment and then they produce at the same exact time an inverted, an upside down wave. And they play both the natural regular wave and the inverted at the same time. And what happens is it cancels itself out. So they have two opposite waves crossing each other at the same time and canceling the sound. Awesome, right? And if you have a pair of noise-canceling headphones, I'm jealous because I wish I did. All right, here's some pictures. Now, these have graphics that move. Your notes that I put on there will not move, but these move, so top pictures are the same, but I thought we could see this here. The two humps come together, and when they come together, they grow and they add together. Now, notice they add together in the exact size. If you put the height of the one wave and the height of the other wave together, that's how high it reaches in the middle there. So they build together. It's also known as reinforcement. Oh, that's not a very good picture for this, but this is destructive interference again. The red and the blue lines are opposite sides, and then the black line is supposed to be what actually happens. And again, if they were exactly the same size on the top and the bottom, they would cancel each other all the way out, and that would be the noise-canceling headphones. But this one is canceled out just a little bit. Destructive interference. Destructive means to destroy or break. Okay. Now, here's some weird things that happen, and this is what the video that we're going to see. I have my a link up here in the notes. You can link to it. I could link to it here, but when I tried to put that link into my video, it did not work. So I'm going to put a little disclaimer here. I'm stealing this from Flipping Physics. So this is not my own work. This is Flipping Physics, and I suggest if you like this guy, his name is Bo. He does a great job of explaining, that you go to his website, his YouTube channel. I subscribed myself. I thought it was awesome. If we were in class, I would just do these things myself. I'd bring in the guitar, we'd get out the tuning forks and just go at it. Okay, well, anyway, what beats are. Beats are when the waves are very close. Now we have two tuning forks there. When the waves are really, really close, but not exactly the same length, they don't line up exactly right. And when you see Bo's video, you'll see when he overimposes them, I can't do that kind of stuff. But what happens is the parts where the waves overlap on the top, they both grow. And the parts where they overlap, one on the top, one on the bottom, they both shrink. And so what happens is this pattern, because the waves don't change, there's this pattern that forms, which it's like a pulse. And you probably hear this, like if you're tuning your guitar and one of your strings is slightly out, you'll hear wom 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 wom. Or if you're singing by someone who's just a little bit out of key, right? It will make that weird little beady sound in there, right? And so again, I'm sorry that in class we would just do these things, but since we are not able to do that, we'll have to watch this video. Okay, let's see. All right, before we go to that video though, let's look at this. This is called a standing wave. Now a standing wave is a very special constructive and destructive interference. A standing wave, if you look at the black line, looks like it's standing still, right? And if you're playing the guitar, I'm using guitar, but this is for all instruments, there are standing waves. Either the strings or the sound waves could be standing waves. And the waves pulse up and down in a regular pattern, but they don't look like they're moving. In real life, they are moving. It's two waves going opposite directions that cause this pattern to form. But all of our notes and things like that are usually standing waves. So the standing wave has two parts. The part that does not move, I'm pointing at the screen like if you could see it, but the part that it looks like it's pivoting at, right? It's at the resting position. It looks like it's just pivoting at that one spot. It's not moving. That's called the node. And you'll see Bo in the video do some harmonics on the guitar where he presses on the nodes. And he has a little video that shows the same kind of thing. And then we have the antinode, and the antinode is the spot that's moving the most. Okay, so the node is the pivot spot, and there's not much energy at the pivot spot. And the antinode is where it's moving the most. That's what would make the sound. If that was a guitar string that was vibrating, you would hear that antinode because that's pushing the most air, and that's what makes sound. Okay, we're going to stop right there, and I'm going to pump in this video, and that should probably be long enough. You'll have a worksheet to do with this, so make sure you do the worksheet as you watch the video. I'm going to go right in order, so it should be pretty easy. Let me see if I can get back up here so we can see. Hey, there we are. So do the worksheet and follow along. I hope you enjoy this. I'm sorry we can't do the demonstration ourselves. Maybe when you guys get back, we'll show you some other stuff with this. All right, hey, have a great day. And this is the awkward part where I try to turn off the video again.
Good morning, I'm Bo. This is my presentation on beat frequency for It's probably best to start by hearing what beat frequency is. So let's start with just a 440 hertz tone. And then a 441 hertz tone. And then let's play those two frequencies together. What you hear is called the beat frequency. The equation for the beat frequency is the absolute value of the difference between the two frequencies, which is why this beat frequency is 1 hertz or 1 cycle every second, and this beat frequency is 2 hertz or 2 cycles every second. And then 3 hertz and so on. Now that you know what beat frequencies sound like, let's make sure you know why beat frequencies happen. When two sinusoidal frequencies are close to one another in frequency, their two wave patterns look like this. Actually, let's overlap the two waves to better understand how the wave interference works. Hopefully you can see that the two waves alternate between being in phase and therefore constructively interfering with one another to create a larger amplitude, and then being out of phase and therefore destructively interfering with one another to create a smaller amplitude. When this happens, the amplitude of the two combined waves increases and decreases at the beat frequency, and that is why you hear beats. We can go back to the original example I had you listen to and show you the waveform for one beat. You can see the waveform for one beat has the same shape as the black wave, which is the superposition of the two waves close to one another in frequency. Again, because both waveforms show beat frequency. The top wave is the audio recording of beats, and the bottom wave is an ideal representation. A practical application of this is that beats are a useful way to tune some musical instruments. For example, on a guitar, the fourth harmonic of the low E string is at the same frequency as the third harmonic of the A string. So this is the E string, and this is the first harmonic on the E string. This is the second harmonic on the low E string. And just so you know, I am holding my finger gently on the string and not pushing down to create a node at this point and to force a harmonic at this point. So this is the second harmonic, the third harmonic, and the fourth harmonic on the low E string. And this is the A string, so this is the first harmonic on the A string, this is the second harmonic on the A string, and the third harmonic on the A string. Therefore, when you play the fourth harmonic on the low E string and the third harmonic on the A string, you should not hear any beats because the two are in tune with one another. However, if one of the strings is slightly out of tune, then what you hear is beats. And what you can do is you can then adjust the frequency so you no longer hear beats and the two are in tune with one another. One more time. So again, if one of the strings is slightly out of tune with the other one, you hear beats, and what you can do is adjust the frequency so you no longer hear beats and the two are in tune with one another. A practical application of beat frequency. Thanks for learning with me. It was fun. Yeah.